Okay, good morning, just everybody. I'm going to talk to you about red dwarf flare stars, and this just a little bit of background to this presentation. This is not my PowerPoint presentation. This was put together by one of the American team members, Bob Buchheim. You'll see the faces in the next few slides. Because this red dwarf star project was his idea. So a very, very similar presentation is being given next week at the Society of Astronomical Sciences conference in America, which is their equivalent to this. So as a member of this project group, I suggested to Bob that what if I was to give a similar talk tailored around your presentation at the Vega 2022 conference. He said, great idea. So what I've done is taken his presentation and added a few things, a few extras to show you. Right, so this is the way the presentation's going to run. I'm going to talk about the genesis and the organisation of the project, the data management and data analysis tools that we've built. This project is in its infancy. It's only been going a couple of years. This was an idea that Bob Buchheim had about looking at red dwarf flare stars and what we as amateurs what science we can get out of it. So it's an example of small telescope science, American, British amateur collaboration. So far we've got about 12,000 spectra in the database, and I'll be talking to you about that as we go. So the next slide. Okay. A flare is a flare. End of. Whatever star it's happening on. Okay, so we go on to the next movie as well. Solar flares in hydrogen alpha. Now, slide number 4. No, sorry, that's not slide number 4, it's the next one. Okay, so just to put into some context what it is we're looking at, this particular star, EV Lac, is in the constellation of Lacerta, near Cassiopeia, and this is an artist's representation of what they think this red dwarf looks like. Okay, so this star, percentage of total stars is 80 to 90%. They're K and M type stars. Their masses are small, between 0.08 and 0.45 for M type stars, Temperature ranges from 2,400 to 3,700 Kelvin. Luminosity 0.08 of the solar mass. The flare style characteristics is that Balmer and Passion lines often in persistent emission, young, fast rotators, typically less than 5 days, fully connective atmospheres, strong magnetic fields of a few thousand Gauss. Now for this particular star, EV Lac, it has a rotation period of around 4.3 days. It's at magnitude 10.09, spectral type M.35, and it's at distance of 16.5 light years approximately. Our sun's average magnetic field is only about 1 Gauss. 75% M and about 12% K for that value. B minus V colour index for the M0 to M9 is 1.4 to 2.2, and the M-type dwarfs show emission lines. So here's a spectrum of the M-type dwarf star. Normal process stacks individual spectra. This is a stack 43 times 240 seconds, taken by one of the team members, Forrest Sims. As you can see, this is a red star with a high output at the blue end of the spectrum. So Forrest is using an ALPI spectrograph, which has a resolution of about 1,000, and with the ALPI you can look at all the hydrogen Balmer lines because they're all subject to flares. You can see flares in quite a lot of these lines. Some hydrogen alpha seems to flare the least, but the hydrogen beta and gamma and delta lines flare up more frequently. I'm looking at this particular line because I'm using a higher resolution spectrograph.
Jack, can I have a question?
Yes.
What was the magnitude of this star?
The magnitude is 10.09.
10.09.
Yeah.
And we see here 43 spectra with
240 seconds.
46 seconds.
Oh. Right. What I should tell you is that...
What was the aperture of the instrument? Because 10 is unbelievable. 43 spectra.
They're using plane waves. They're using 20 centimetre plane waves to look at it, right? Now, because the flares can be 5 minutes or so in duration, the maximum exposure you want is 5 minutes. So, in my case, it's always 5 minutes. So I'm clocking over 100 spectra a night with an 7-8 hour observation run. Fortunately, it's there at the beginning of the observation run, then it's over there. So we've been very lucky with some of these. There are other candidates I'll tell you about. It's visible all night. So I just do a meridian flip an hour and a half before it's due, and then go to bed, get up in the morning, and there's your data. We have to take short exposures otherwise we're not going to see a flare event. Okay, so this is what I'm doing in my observatory. This is the raw image. This is as you would see it downloaded from the camera. There's the hydrogen beta line, and there is the hydrogen beta peak. I'm looking at a resolution of about just under 4,000 with the LIRES 3 spectrograph. I have all 6 gratings. They have the 300, 600, 1200, 1800, 2400, and I left out the 150. So I'm currently using the 1200 grating.
In LIRES 3?
With the LIRES 3, I'll show you a picture, and it's got the higher the lower the resolution of the gratings, the faster they are for this kind of work. I do experiment between the 12 and the 1800, but the 1200 works best for this particular setup. That might be a cosmic ray hit. I have no idea what that is. I'll try to make it correspond. Maybe it's that. Maybe it's that. I don't know. But you get these artifacts coming in into the images, but it's all filtered out. This is what we're interested in. Yeah, there's a fair bit of noise in the spectrum. It's 10th magnitude, and we are looking at stars under 11th magnitude. 11th mag is the limit for these instruments. So what happens is this is the clever bit now. LIRES 3, 23 micron slit, 1800 grating, 300 seconds. You get a resolution of about, I think that actually should be 18,000, not 1800. I've just noticed that error. I'll have to correct that. The only things that change with this setup is the slit and the grating, depending on which line you're looking at, and you have to experiment. Otherwise, the setup is never ever disturbed. So I have to. This is the result of an experiment with the 35 micron slit and the 1800 grating. You get a resolution of about 10,000. That should be 18,000. I think we decided to go with this one instead, and also with the 35 micron slit, you get more light coming into the spectrograph. Everything in spectroscopy is a compromise, so I'm able to get that kind of detail. And I guess I'm not sure whether this is noise or part of the spectrum. Okay, so we have a team of collaborators, 10 of us, 2 in the UK, 6 in the USA. Now, what is the beauty of this type of collaboration? Anybody? There's one particular advantage. Can anybody tell me what it is?
Latitude distribution. Latitude distribution?
Yes. Okay, so what that means is the time difference is like they're 7-8 hours behind in the time difference. When I finish observing in the UK, they start observing in America. So we've got good coverage, which greatly increases the chance of a flare detection. So the other targets are AD Leo, BY Draconis, and currently CR Draconis. Now, the thing about CR Draconis is that we have a professional astronomer, Dr. James Jackman, He was at University of Warwick in England. He's just moved over to the University of Arizona, and he gets time on the TESS satellite to look at CR Draconis, and he's giving us all the information of the timetable of when TESS is going to get spectra of CR Draconis, and it's really is a short window of observation for the satellite. And so what we're able to do is look before, while the satellite is taking images, and after the satellite is finished doing its imaging. So we can cover it before and after the event, night, and we can cover it any other clear night when TESS isn't looking at that particular object. That's the latest one. There are other candidates coming along. We haven't had much success flare-wise with CR Draconis. Some nights you're running for 5, 7, 8, 7 hours, nothing. Other nights you get flares. Nobody knows the periodicity of the flare of CR Draconis. AD Leo, by contrast, is the most famous flare star of all, and that's looked at as well. And professionals are looking at these flare stars, but there's not enough coverage of them, which is why we've got involved. So here are some faces. This is Al Stewing in America, and this is his setup, and it's very high up actually. The pier is very high up, and he has to get up a ladder to make all these adjustments. This is my setup in the UK. This is Forrest Woody Sims setup in Phoenix, Arizona, and here is our brainchild Bob Bookheim in Arizona, and he calls that the Lost Gold Observatory. So you can see that would be a plane wave. These are Celestron C14s. So that's 4 out of the 10 of the group people that you can meet. Okay, so this is my observatory in the UK, called the Huggins Spectroscopic Observatory. Sir William Huggins was a Victorian amateur astronomer and pioneer in spectroscopy, and he had his observatory. He was working from about 1860 to about 1900 or so. He died in 1910, and I just decided to name my observatory after Huggins. The observatory was in Tulse Hill in South London, sadly no longer there, long gone. The artefacts, bits of the observatory have ended up at Cambridge University, Institute of Astronomy Library, and Wellesley Women's College in Boston, Massachusetts. His wife gave some of the artefacts, bits and pieces, stained glass and stuff, to the Women's Institute over in America, so it's all over the place. Okay, so just a brief look at the setup. So this is the 4-inch refractor with an Attic 314 monochrome camera. This is the guide telescope. So it's all computerized down here. There's actually three computers going. So I'm looking at the target image on one screen, but I can also flip mirror and look at it visually if there's an issue with the camera or the computer. And I've had a few issues with computers going down. The computers are the most unreliable pieces of the chain. I've not had any issues with the cameras so far. So this is the C14, Celestron C14. That is the Paramount MX. that's the science camera, the Attic 460 monochrome, and that's the Lyra's spectrograph. And that's the setup I'm using at the moment. And this has been operational since 2013.
Have you not got the guide camera on the side of the Lyra's as well?
Ah, yes. That's the Lodestar 350 guide camera. Sorry, I forgot to mention
Because
that.
you said you were guiding with the refractor. I didn't quite.
Right. What I should have said was that looks at the target. I'm not guiding with that refractor. I'm guiding with the Lodestar. I'm guiding on the star using PhD2. This is just a very convenient way of looking at the target. I'm looking at the computer screen. I'm not looking through a telescope. It's all computerised. So the screen's up there, the target screen. Yep, on target. I can see the object. Off we go. Right. Okay. So slide number 7. We have bi-weekly Zoom meetings about the updates and project progress of the Groups IO team. And this is for the coordination, the document sharing, reference material, progress reporting, help solving problems. Quite a lot of problem solving goes into this. We share the Google Sheet, and which was an attempt to manage large numbers of spectra. We're now looking at other ways of saving the spectra as time progresses. We just keep getting more and more spectra. Some of the guys will cover photometry as well. I don't do photometry. I just do the spectroscopy, and it gets recorded. This is something that Sean Curry, one of the, he writes some of the software. He's written this guide to spectroscopic and photometric observations, spectroscopy, no flare, possible flares, photometry, no flare, possible flares, data collected, not yet examined, and it's coded so that we can see what's been picked up and what hasn't occurred over nightly observations. Now this is one of Gary Walker and Frank Parks in America. A stellar flare caught in a B photometric filter. What does a flare look like? Well, here's an example of what a flare looks like photometrically. In this case, there are two flares, here and here, caught by Gary Walker and Frank Parks. Gary Walker's on the eastern seaboard, near New York, and Frank Parks is on the western seaboard, San Diego, down California. So coverage is very wide. They used the AAVSO, Association of American Variable Star Observers, photometric database as our repository, so that the AAVSO are allowing them to put their photometric observations on their database. So thank you, AAVSO. The same as the British Astronomical Association will allow its members to put their spectroscopy observations on their database, and they also do photometry. slide number 9. Okay, so here we see the hydrogen alpha emission line change during a stellar flare. So this is what's happening. It flares up for a short period of time, and then it drops off again. Spectroscopically, we'll identify a flare by changes in emission lines of hydrogen, calcium-2 and helium. Similarly to the photometry, spectroscopy splits the light into its constituent wavelengths. In other words, it shows the intensity as a function of individual wavelengths rather than the combined wavelengths included for a B filter. So if you get two spectra apart and combine them and you see that and you see that, there's a pretty good chance that you've got a flare event. Flare detection with spectroscopy and photometry. Here we see what we detected the same two flares, one with spectroscopy and one with photometry. And this is the way they interpret whether or not a flare event has occurred. But we can actually sort of, it's a double checking system if you like. If you think you've got a flare at that MDJ, mid-Julian date, mean Julian date, and people are also looking simultaneously with photometry and they see a brightening, we can actually match these up using those photometric filters, and we can then look at equivalent widths using the software that they've developed in America to do this, and we can actually nail it down using that as we can cross-check the results and match them up. There's the date, there's the corresponding date spectroscopically. Yes, we've got a flare. It says here in the subnotes, which you can't see, the careful viewer may see a small time offset where the flare peak in spectroscopy lags the peak in photometry. Right, so we've got the hydrogen Balmer emission line equivalent width during the stellar flare in EV Lac. So we're using equivalent width on the x-axis running along here. A significant amount of flares, total energy is released in the blue and the NUV wavelengths, while M dwarfs are relatively dim as mentioned earlier in these wavelengths, resulting in increased flare contrast. As you see, the hydrogen alpha has the smallest hydrogen alpha has the smallest flare in EW. That doesn't flare very often at all, so we still cover it just in case. But the hydrogen delta shows the highest increase in equivalent width. So you've got the minimum equivalent width and the highest equivalent width, hydrogen alpha and hydrogen delta. Right. Flare analysis metrics. Well, what does this mean? Metrics is being used as a generic term for properties that we can measure in our observations, including properties of individual events, equivalent width, flux, B-band magnitude, etc., statistical properties, flare rates in flares per hour, and calculated properties, flare energy in ergs. There is quite a bit of mathematics associated with this as an aside, but I don't think there's anything in this particular presentation. It's fairly simple mathematics as well, depending on how good your knowledge of mathematics. So this is the one particular flare duration, and you can see rise times, decay times, and using a bit of simple mathematics you can work out how long the flare is. SpectraStats user interface. This is for analysing 1D flare spectra. All spectra are processed as 1D spectra and uploaded onto the Google Drive. We're all singing from the same hymn sheet in that we're using ISIS. Some of you will be familiar with that French program from Christian Buell to process the spectra. Fortunately, ISIS can be configured to report on individual spectra. I can get about a batch of 60 spectra processed in ISIS individually for hydrogen beta line, and if I get 100 spectra in 120 spectra in one night, I do the processing in 2 separate batches and then upload the 1D FITS files onto the Google Drive. So I keep all my data on external hard drives, so I get the individual spectra processed, and I could look at them in plot spectra as well, and that shows initial results whether or not you've got a flare event. But more then the data gets uploaded to the Google Drive, and Sean Curry and Woody Sims then use their software SpectraStats to do more advanced processing on the data to pinpoint any flare events. So what they did was they devised the hydrogen beta 3 sigma test for a flare. The way it works is there are plots. These are plots of hydrogen beta from SpectraStats showing a very obvious flare using equivalent width versus Julian date. SpectraStats, this piece of software that these guys developed over there, calculates statistical data on the processed 1D spectra that is used to provide an initial measure of a the statistical significance of any changes in equivalent width over the observing session. Here, the flare is obvious as the standard deviation plot greatly exceeds the 3 sigma threshold level. So that's basically, it's a statistical process for looking at it. We have been advised to raise it to a 6 sigma threshold, and they're working on that now, just to tweak the process and make it more sensitive. So what this shows is standard deviation values for each wavelength bin. Then it's they've devised using Python software. I'm not sure whether this is a movie or not. No. This is a surface plot that they've devised, and what that does is shows the active and quiescent periods of the flare event, and it's actually in 3D, and you can move this surface plot around, rotate it upside down, inside out, and look at it from various different angles. You can look at the geometry of what's going on. So that's the flare there that's occurred. So it's quiescent down there, up it flares, there's the timer, and then rest of the night, if you like, it's quiet. So someone picked up a flare at the beginning of the observing run. You could pick up a flare in the first 5 minutes and have nothing else all night.
I think the time is reversed. I mean, it's the right, it's the later part, and you're starting with the quiescent and then it flares.
Oh, here? Yeah, okay.
If you look at the numbers.
Oh, not, yeah.
Jack, is that the same double peaked event that we've just been looking at on the graph? There's a hump and then there's a bigger hump.
Possibly,
Right.
yeah. Thank you for that. Yeah, I'm not looking at that. I was just looking at this. So that's the quiescent part there, and then right towards the end of the night, we got a flare. Oh, right, okay.
Oh yes, yeah.
It works. Yeah, look at that. Oh. This is written with Python code. I think that's a pretty clever piece of software. Equivalent width analysis, user interface. What does it say about this? Okay. We started off with a simple question: how many flares did we see? We had accumulated a large number of spectra. The count flares we needed to identify peaks in EW that exceeded some thresholds above quiescence. We started using Excel to read the CSV files that were output from SpectraStats for each observing session. With 3 sets of eyes, we attempted to define criteria for identifying a flare in a data set. Just about the time we could agree on how to visualise quiescence, we would encounter the next observation data set and wonder if we had made the best choice on earlier data sets. After a few days of this, we realised that we were doomed. This process had no flexibility or repeatability. We realised that we could load all of the data set CSV files from all of the observations for all the targets into a database. Then we could choose criteria for calculating quiescence, which meant that we could also test different definitions with different values. This will take on more importance in the future as we want to do more than just count flares, but also attempt to estimate their start time, end time, and EW ratios.
Jeff, can I have a question again? Is there any knowledge about the individual error of processing of the several observers itself?
Not at
If I understand your presentation right, there are each
time.
every individual observer, spectroscopy observer, processed his own data. But that leads me to the question: is there some knowledge about the individual processing errors of the individual observer?
Yes, because they're all we're all using the same processing data reduction software, ISIS. So if we took a deep dive into that, yes, we could detect that. But provided we've all got ISIS configured in the same way, in theory there shouldn't be an issue. This would be a software issue, wouldn't it? In theory that shouldn't happen, but it depends what version of ISIS you're using. Things can change in ISIS. I'm using the latest version, the other guy's using the last version, but by and large it's been pretty consistent. Yeah.
Well, the general exercise would be, if you have 4 processors on the same data set, and then compare whether you come up with the same result, or if not, that will give you some kind of idea what the human or generic error is.
Yes, that's right.
So
The only difference with that is that I'm working at the highest resolution with the LIRES, just under 4,000. These guys are working with the LISA spectrographs. Someone's working with an ALPI, 600, 1,000 resolutions. So you've got systematic errors in the spectrograph to contend with. So it won't be the software, it will be the stability of the spectrographs that could be causing an issue. You had a question? Yes?
When you determine the properties of the flares, you measured the rise time and the length, the duration of the flare. To me, the flares which you showed the same behavior, this FRET behavior, so fast rise, exponential decay, as, for example, in X-ray flares of neutron stars. So this is completely different physics, but did you calculate if there's a dependence on the property, or is that an exponential decay, and what would be the exponential decay time for the flares? Do they scale with intensity? Do they scale with something else? Did you look at that?
So far as I know, that has not been looked into. But I would like to afterwards make a note of your suggestion and feed that back to the team in America who do all this more advanced analysis. Yeah, okay. Right, next slide. Yes. EV Lac hydrogen beta equivalent widths for all observers. MJD stands for modified Julian date. So here is our first product from the database, a plot of equivalent width against modified Julian date for EV Lac that includes all the team's observations for this season or a previous season. Each red dot is an equivalent width measurement, and it varies quite a bit. There are over 3,200 spectra equivalent width measurements displayed in this plot. 195 hours in 73 observing sessions. Equivalent width analysis allows us to identify criteria for a quiescence level and automatically calculate a threshold. Actually, we can set multiple threshold levels and infer flare candidates where spectra peak equivalent widths exceed the threshold. Equivalent width analysis and the SQ with the SQ-Lite database allow us quickly and easily to vary assumptions and databases. We can chop and change. We will be adding the other candidates, as I said earlier, AD Leo, CR Draconis, and future Red Dwarf flare targets to the database. The exploded view. This is like an exploded view named by the person who put together the PowerPoint presentation. That's what he calls it, exploded view, equivalent width versus MJD plot. This really, what that means is it's magnified or zoomed in on the interesting region. And I think that is the subject of the next slide. Yeah, sorry about that. I was racing ahead of myself. Exploded view. I'll just run by that again. It really means magnified or zoomed in on the interesting region, showing that the minimum equivalent width is not constant from night to night, and this complicates the assessment of the quiescent equivalent width level. And these are equivalent width ratios and distributions for hydrogen alpha, hydrogen beta, hydrogen gamma, hydrogen delta. Total detected flares per hydrogen Balmer line, which this sort of puts it into quite nice context. Hydrogen alpha just gives 10. Hydrogen beta 31, that's the line I look at all the time. Hydrogen gamma 30, and hydrogen delta is the one that gives the highest frequency of flares, and that's the way they've put the data into flare equivalent width ratios and distributions for all observers.
How many of them did you observe in several lines at the same time?
Oops. Has this gone?
Just about.
Sorry, what was the question?
You showed that in H alpha, beta, delta,
Yeah.
you observed 30 and 34.
Yeah.
How many did you observe in the same line simultaneously? Not in the same flare in different lines.
Only what? My answer to that is only what you can see on that slide sheet. If that's your question.
How many did you see in several lines, so that it's certain that they are detected?
Oh right. Well, that is the degree of certainty that we've got from a sample. Yeah.
Yeah, but so the H alpha just 10
Yeah.
means that less observers observe H alpha.
In that set of observations.
Every flare shows up in all the lines.
Yeah. Yeah. The flare shows
don't
up.
have one line perspective, okay? Yeah.
No, the flare shows up in all the lines, but that hydrogen alpha is the least frequent of the lines because it's H alpha, and hydrogen delta shows the most number of flares. But when the flare event occurs, it occurs in all of the hydrogen alpha lines, least of all the hydrogen. hydrogen Balmer lines, least of all H alpha.
So, but you only see either H alpha or H beta in one spectrum. You don't have both Balmer lines in one spectrum.
Yes, yes, yeah. The guys that are covering it with the LISA see all the hydrogen Balmer lines from hydrogen alpha down to H gamma. They could actually make a movie in ISIS of the flare events jumping up and down. The reason I'm not seeing it in my spectrograph is because I'm looking at higher resolution and I'm concentrating on the hydrogen beta line because the gamma and delta and gamma hydrogen Balmer lines are too blue for the sensitivity of the grating of the LIRES spectrograph. I won't get anything interesting, let alone be struggling to even see them. But because they've got lower resolution, they can see the whole spectrum. That's about as... yes, I can do hydrogen gamma. I will get a result, but even less chance. The further into the blue you go, the loss of sensitivity goes down with the gratings in the LIRES. So that's the one I look at now. What happens next? There are professional papers published on these flare star events. There's not many papers published. It's not widely understood. For the amateurs, it's a really new area of science, and these are the sort of results people are getting. And what we're doing is we're building up a bank of a library of professional papers that have been published over the years by professional astronomers.
So the paper by Leitzinger, which data is it using? Which spectrograph?
This is what we're trying to achieve results-wise. Yeah, putting it into context, what is the team trying to achieve? I just want to draw your attention to Bob Bookheim's comments at the bottom of this slide that he sent me to include. These are two papers here, and Bob says these two papers, what we might hope to see in Jack's high resolution spectra some night when fortune smiles on us. Enjoy, Bob B. Thank you for listening. Questions that I can't answer.
So you showed a slide where you compared the spectroscopy with the photometry of the flare, and you read a comment that said something like, you'll see a delay in the spectroscopic data from the photometry, and I was left hanging for the explanation.
I don't know why you would get that delay, but I will take that as feedback and put the question to the people in America. In theory, you shouldn't get a delay, should you? You've got two observers observing the object at the same time should get consistent results. That's another question to ask them. Anybody else for questions?
Maybe a practical question. You showed us 4 stars which are chose to observe. So one was motivated by the test campaign. So what are the selection criteria for the stars which are looking at?
Right. Selection criteria, for example, in AD Leo, It's the most famous flare star of all, and we're guaranteed to get some science. That's the selection criteria. So the targets are AD Leo, CR Draconis, EV Lac, and I forget the name of the other one, but it's here somewhere. BY Draconis. They're all known to give flares, they're safe bets, right? We've not had much success with CR Draconis. We've only just this season been monitoring CR Draconis. So this is the first year of data that we've got. That's because Dr. Jackman in America has got time on the test satellite to look at it, and he's asked us to join in and look outside the observation windows. But we've not had much success flare-wise with that particular star yet. And Dr. Jackman is looking at other candidates below 11th magnitude that we could observe in the coming years. This is a long-term project, and we're going to build up an atlas of flare star spectra and photometric data, and that beggars the question, where are we going to keep all this data so that someone can, a professional astronomer can data mine it in 10, 20, 50 years time? Will the cloud exist? I don't know. So we've now got to look at ways to preserve the data for the next 100 years so that it's going to be stable and not disappear. That's one of the other things that you've got to consider. We get, and professional astronomers as well, like with the Gaia satellite that's giving us the structure of the galaxy, the amount of data that's coming down night after night after night, not terabytes, bigger yettabytes of data, and they haven't got the staff, the people to sit there and go through it. So they go out to the amateur community to look at the data, as with the Galaxy Zoo with Chris Lintop from The Sky at Night. He's opened it up to amateurs to look at the Galaxy Zoo. And we're going to be getting even more data now with the James Webb Telescope.
When you say tests, is the 2-minute cadence or the 30-minute cadence?
Sorry?
Which time did he apply for?
Oh, I don't
the
know.
The short cadence or the long cadence?
Short cadence, yeah.
Okay, thank you.
Thank you.